Now let's talk about how vaporization occurs and what kind of energy, how energy moves when it comes to vaporization. Vaporization seems backwards when you first hear about it. Vaporization is actually an endothermic process. So what does endothermic mean? Endothermic means the system is absorbing heat. So whatever the liquid is going to have to absorb heat. That means because energy input is required, so you need to put some heat into the liquid in order to break apart those intermolecular forces. Now, condensation, which is the opposite of vaporization. So vaporization would be liquid to gas. Condensation is the other way, gas to liquid. It is exothermic. It's exothermic, so we release heat because energy gets released when we form these stable intermolecular forces or bonds. They're not actually bonds, that's why they're in quotes, are formed. Now, there is a value, and it is called the heat of vaporization, and it is abbreviated as delta H vape. Delta H, so heat of vaporization, is the amount of heat that's required in order to vaporize 1 mole of liquid. So pay attention to the units here. So your vaporization, so here, again, it's a phase change. So pay attention to your states. So to go from liquid form of water into gaseous form of water, the heat of vaporization is positive. That means we have to add heat. So that would be 40.7 kilojoules per mole plus the water. So here heat is a reactant in order to make the gas. It's temperature dependent, so depending on kind of where you start or finish. But so this is the normal boiling point of water, so this is where it tends to occur. So positive 40.7. So now let's actually do some calculations. Again, after some of the crazy calculations that y'all have done before, this is not going to be that difficult. So let's talk about if we have how many grams of water can we vaporize if we have a total of 155 kilojoules of heat. Start with what you know. 155 kilojoules. Here's our heat of vaporization, the boiling point of water, 100 degrees, is 40.7 kilojoules per mole. Now, are we finished? No, we're not, because it says calculate the mass of water in grams. How do we get to grams? I do hope you said, Dr. B, we use the molar mass. So how much is 1 mole of water? I really hope you said 18.02 grams. If you didn't know that, let's use 1.008 times 2 for hydrogen. So 18.02. Bit of a glare. So now we have that. So let's multiply by 155, divide by 40.7, and that's going to give us 68.6. 68.6 grams of water. So look, this is a short problem, super easy. You can do these. Okay, let's calculate the amount of heat in kilojoules that we need to vaporize 2.58 kilograms of water. So here, 2.58 kilograms. Now remember, heat of vaporization, positive 40.7 kilojoules per mole. So we got to be in moles here before we can do things. So before we can get to moles, we got to get to grams. So 1 kilogram is 1,000 grams. See, you still got to know your conversion factors. And we know we said 18.02 grams is 1 mole. And we know that for every 1 mole, it takes 40.7 kilojoules of heat. Grams, moles, everything cancels. We're left with kilojoules. That's what we want. Let's calculate. 2.58 times 1,000 times 40.7, and let's divide by 18.02. So that's a lot. 1, 2, 3. So we can say 58.27 kilojoules, or you can say like 5.83 times 10 to the third kilojoules, something along those lines, if you like scientific notation or not. One more. Suppose 0.48 grams of water at 25 degrees Celsius condenses on the surface of a 55-gram block of aluminum that is initially at 25 degrees Celsius. If we don't lose any heat, what is the final temperature of the metal block? So here's our heat of vaporization, and we also have a specific heat. So this is going to be a two-part problem. You may have to go back and review some of the thermochemistry concepts. If you need that, please look at my video on that. Heat exchange would be the topic. Maybe I'll put in a link to it. So first of all, let's figure out how much water we have. So we have, and let's figure out what the heat associated with is associated with that. 0.48 grams of water. Now remember, we got to be in moles. 18.02 grams of water is 1 mole. Now here, this is condensing. So when it condenses, it releases energy. So this is going to be negative now, the number that we put in. So we know that 1 mole of water is going to release, the negative means release, it goes out of the water into the environment. It's actually going to go onto the metal. 44.0 kilojoules. Okay, so now let's figure out how much is released. So here we have 0.48 times negative 44 divided by 18.02. So that would be, let's go with negative 1.17. 1.17 kilojoules. So that just means it's released. Now the problem says if the heat released only goes towards heating the metal, so we don't lose anything, that'd be our aluminum block. What is the block? So that, remember now, the heat that is released from the water is, so we can say Q of the water. So the heat that's released by the water is gained by the metal. So the negative of negative, or well, so the water loses 1.7, so the heat that's gained by the metal is the same amount, so Q metal is 1.17 kilojoules. All right, so now let's use our other heat equals MC delta T. Hopefully you remember that. All right, let's plug and chug. So 1.17 kilojoules would be what, 1170 joules. Go ahead and convert to joules. Our mass is 55 grams. Our specific heat of aluminum is given in the problem, 903 joules per gram degree Celsius. And we need to know what our final temperature is if we start at 25 degrees Celsius. Now, I went ahead and did that because specific heat is in joules, so I need to make sure that all my units match up. So grams are going to go away. Okay, so here, I'm going to multiply 55 by 0.903. Again, how you choose to approach this problem is going to be maybe a little bit different. 49.7, that's joules per degree Celsius because the grams go away, times TF minus 25. Now I'm going to divide, so 1170 divided by that. So that gives me 23.56 degrees Celsius equals TF minus 25. So now let's add 25 to both sides. And so depending on how you round, I got 48.6 degrees Celsius. If you want to round up to 49, that's fine. Show me your work. And we're good with that. So here, how you can use, heat calculations and combine them.